whenever the part of external ballistic ends, the terminal ballistic starts. That means the target must touch the projectile before the terminal ballistic starts. As soon as the projectile reaches the target, it may penetrate the target or it may just bounce, and this bouncing is called ricochet of the bullet. Ricochet of the bullet is a very important phenomena in ballistics, and it causes several important effects on the bullet or the path as explained by me now. Number one, the bouncing effect would result in the change of the trajectory. The trajectory will no more follow the path already followed, but will get changed. The second aspect would be the decrease in the velocity of the projectile. The original energy of the projectile gets decreased considerably to the extent of even 1/3 of its original energy. This decrease of energy causes decrease not only in the velocity but also in the range, firing range as we call it. The third aspect of the ricochet is that the angle of incidence also gets changed. The fourth is as soon as the target gets touched by the projectile, it results in losing of the gyroscopic effect of the bullet, and this loss gives rise to tumbling of the bullet. The fifth important point which I like to say is that the surface of the target also plays a very important role in the ricocheting of bullet. So far as the construction of the bullet is concerned, the shape of the bullet also plays a very important role. For example, a round-shaped bullet can be easily ricocheted, whereas a square type of bullet will not give rise to ricocheting but gives rise to penetration. Thus, it is important aspect is study of ricochet. Ricochet sometimes has resulted into fatal accidents, and they have been described in the main paper Terminal Ballistics Part 3.
After studying this module, you shall be able to know about Ricochet phenomena and its effect, analysis of ricochet and its various affecting parameters, principle of bulletproof jackets and vests. Ricochet. Ricochet phenomena refers to the deflection of projectile from its trajectory or line of motion after hitting a hard object even when from bones. Whenever a bullet is fired on a target, it will either penetrate or bounce off and continue at certain angle, and when it bounces, deflects, it produces following effects. The trajectory of bullet effectively gets changed. Apart from the fact of changing direction of motion of the projectile, The angle of deflection also undergoes a substantial change. After ricochet, the projectile tends to lose considerable amount of its energy, which may be anything up to one-third of its total energy. It loses gyroscopic stability and may tumble after ricocheting. The range will decrease, which is in contrary to the popular belief that a ricocheting bullet will have the elevation for maximum range. The projectile may carry some material from the surface of the target after ricochet. Critical angle and ricocheting angle. The actual degree at a bullet producing ricochet from a surface is called the ricochet angle, and the minimum angle at which the bullet may produce ricochet phenomenon is known as the critical angle. Prediction of the critical angle for any bullet surface configuration is, however, extremely difficult. Factors such as bullet shape, construction, velocity ricocheting surface all have a pronounced effect on the outcome. In the above figure, angle A refers to the angle of incidence and B refers to the angle of deflection, ricochet. On ordinary ground, the bullet will generally penetrate if it strikes at an angle greater than 15 degrees. But there is nothing certain about this, and a dogmatic statement as is what the angle is beyond which a ricochet will not occur should not be made, for it is always possible for the bullet to strike a slight regularly in the ground which will greatly change the actual angle at the point where the bullet touches the surface. The same effect can be produced by the presence of a small bullet at the point where the bullet strikes. The tendency to ricochet is very much affected by the shape of the tip of bullet. A round pointed bullet will tend to ricochet easily than other shapes. Analysis of ricochet. Affecting parameters. The potential to ricochet is so diverse that it is nearly impossible to lay down any firm and fast rules. However, there are a few generalizations which may be applied. Anyhow, the ricochet of bullet strictly depends upon the state of the target object. The evenness of the surface also plays an important role in ricocheting of bullet. In most of the cases, the angle of ricochet is considerably less than the angle of incidence, but it is not so in all cases, especially with hard projectiles. Jacketed, high velocity projectiles penetrating a frangible material such as stone or concrete. The critical angle for a soft or hollow point bullet is lower. For an equivalent fully jacketed bullet, it would appear that the collapsing hollow point nose increase the incident angle, thus increasing the propensity for ricochet. The critical angle for a given bullet type target medium is not velocity dependent. Bullet will invariably lose its gyroscopic stability and tumble after ricocheting. The tumbling gives rise to a distinctive whining or whirring noise as the tumbling bullet passes through the air. Bullets which have ricocheted from glass, steel, concrete, or wood have a very distinctive of the material where the contact has been made. The contact point will often have wood, fiber, or concrete adhering to it for easy identification if the material was glass or polished steel. The mirror-like surface is quite distinctive. This is not However, the case with a bullet which has ricocheted from water. Even with hollow point bullets, it is differentiated between a bullet which has ricocheted from water and one which has not. Wounds and ricocheting. Wounds produced by bullets ricocheting from hard surfaces can be easily identified. The entry hole caused by a bullet after ricocheting will be very distinctive, as it is caused by a distorted bullet which will generally have ragged edges. After it enters the body, the bullet, due to its inherent unstable condition, tumble end over end and would leave a large and irregular channel. Jacketed bullets tend to break up on ricocheting, and possibility of recovery of fragmented jacket and lead core are more. High-speed bullet with a thin jacket, for example, .223 or .220 Swift, will invariably break up before ricocheting. Fatal wounds and ricocheting. Ricocheting of bullets cause serious injuries, even fatal ones. It is well established that after ricochet, the bullet substantially gets deformed in case of lead or gets fragmented in case of jacket. The rag shape of bullet then is capable enough to produce devastating effect, and the entry wound may be fatal. Billiard ball phenomenon and dum-dum bullets are good examples for producing fatal injuries. Case related to fatal injuries and ricocheting. A notable example of the power of a ricochet was given by the fatal accident which occurred in the fall of 1933, when an actor, Russ Colombo, was accidentally killed by the explosion of the charge in an old muzzle-loading pistol which was being kept as a curio. According to newspaper accounts, a friend of the actor snapped the head of a match on the nipple of the gun, which was thought to be unloaded, and it went off and the bullet struck a piece of furniture and then bounced and struck the actor, causing so serious injuries that it resulted in his death. In another famous police encounter case in India, it was alleged by the appellant that the deceased was shot intentionally in the crucial neck portion. However, forensic analysis revealed that even though the police officer fired the shot but not at the deceased, the trajectory was around 1.5 feet far off from the deceased, but the 9 mm jacketed bullet ricocheted from the laminated wall and hit the deceased at the neck region. The critical measurements and crime scene reconstruction made possible to find the factual condition. Bulletproof jackets and vests. One of the tasks the forensic examiner is often called upon to perform the testing and evaluation of bullet-resistant vests and jackets, generally called soft body armor, as this aspect comes within the realms of terminal ballistics. It would be a good point to review the subject. History of body armors. Body armor in the form of metal plates was widely used during the time of hand-to-hand combat with swords, knives, and various bludgeoning instruments. With the advent of the crossbow and firearm, the plain steel suits were found inadequate to defeat the projectiles, and they rapidly became obsolete. During World War II, ballistic nylon, a copolymer of the basic polyamide, was good against shrapnel from munitions. This was, however, of little use against bullets other than low-velocity soft lead projectiles. The major advance in soft body armor came with the generation of what are loosely referred to as superfibers, which were introduced by DuPont. The best known of the was a para-aramid fiber is Kevlar. which was originally used in fabric braced radial tire. It did not take long, however, for it to be realized that it could be woven into a fabric which was so strong that it could be used in bullet resistant soft body armor. The Kevlar fibers were simply woven into sheets with varying thicknesses of yarn and density of weave called denier to provide the particular properties required. The sheets were assembled into ballistics panels, which were permanently sewn into a carrier in the form of a vest. It is undeniable that Kevlar does produce a very effective, lightweight, and flexible jacket which can be tailored to stop virtually any handgun missile. It does, however, suffer from a number of problems. Firstly, it is not stable to UV light and has to be kept inside a light-proof pouch. It is also very susceptible to attack by many household chemicals, and thirdly, if wet, it loses most of its ability to stop bullets. A recent development in the field of soft body armor is the use of an ultra high molecular weight polyethylene fiber called Spectra, which is produced by Allied Signal Inc. This consists of exceedingly fine spun fibers of polyethylene. These fibers are laid in dense mats at 90 degrees to each other, then covered top and bottom with a thin sheet of polyethylene. This is then heated, treated to semi-melt the fibers together or bonded with a plastic resin to form a sheet. With the thousands of bonded fibers which must be pulled from the matrix to allow the passage of a bullet, the sheets are even more efficient than Kevlar. This material is not affected by water, nor is it affected by UV light or any chemical, and it is considerably lighter than Kevlar. If it has a disadvantage, it is that its melting point is much lower than Kevlar. Mechanism of bullet resistant material. To effectively stop a bullet, the material must first deform the projectile. If the surface area of the bullet is large enough and the material has sufficient resistance to the passage of the bullet, then the energy transfer to surrounding fibers can occur. A non-deformed bullet will merely push apart the weave and penetrate. If the bullet is sufficiently soft, that is plain lead, semi-jacketed or thinly jacketed bullet, then the material alone will often be sufficient to cause the deformation. If, however, the bullet is heavily jacketed or of the metal penetrating type, then some intermediate, much more rigid material will be required to deform the bullet. This generally takes the form of a hard plate which fits in the front of the soft body armor. Ballistic inserts. This is the name generally given to rigid plates which are placed in front of the soft body armor. Their purpose is to break up high velocity, hard jacketed and metal penetrating missiles. Once the bullet's velocity has been reduced and its shape deformed, it will be easily stopped by the underlying Kevlar or Spectra material. These inserts are generally made from either a fused ceramic material, heat-treated aluminium, hardened steel, or more recently titanium. These can be either solid plates or small overlapping tiles. Case examples. Soft body armor is not infallible as the following two cases illustrate. The first involved a police officer wearing a very substantial bullet-resistant vest capable of defeating .357 inches Magnum and 9 mm PB bullets. He was shot at close range with a .45 to 70 rifle, which has a large soft bullet weighing 400 grains at a velocity of 1500 fps. Though the jacket was successful at deflecting the bullet, it was driven into the officer's chest, killing him. The second case involved a live demonstration of a ballistic insert plate made of metal. The plate was designed to defeat an armor-piercing round, but the demonstration was merely to show how effective it was against a full magazine from a submachine gun. The soldier wearing the jacket was not killed, but the fragments generated by the bullets breaking up on the plate nearly severed the lower part of his jaw. Summary: the deflection of bullet after hitting a hard object at certain angle is known as ricochet of bullet. The projectile may carry some material from the surface of the target after ricochet. On ordinary ground, the bullet will generally penetrate if it strikes at an angle greater than 15 degrees. The tendency to ricochet is very much affected by the shape of the tip of the bullet. The entry hole caused by a bullet after ricocheting will be very distinctive, as it is caused by a deformed bullet which will generally have shabby edges. The Kevlar fibers are woven into sheets with varying thicknesses of yarn and density of weave, called denier, to provide the particular properties required.